Okay, so if we were going to provide Lewis structures, like I said, we're going back. Okay, how would we provide the Lewis structure for this compound? While we go through, put in our carbons. We could put our hydrogens evenly around it. Okay, do we have our octet satisfied? No, and if we counted our valence or our electron count from C2H4, what would we find? We're missing 2 electrons. Where do those 2 electrons need to go? Into the double bond. Okay. Are there other ways you could have attempted to put this structure together? And you might have tried something along these lines, and you would find that you'd run into trouble pretty fast. Okay. So it's a question of putting the pieces together and seeing the easiest way to do it, okay, or the most natural way to put it together. Okay. So we can look at a Lewis structure of this. So how many electron groups are around the carbon? How many bonds are around the carbon? 4. How many electron groups? 3. Why are there only 3 electron groups and not the 4 for the bonds? That double bond, that pi bond, is occupying the same space or the same relative space as the sigma bond underneath it. Okay? So we classify those in the same group. So this ends up being, you guys are just showing off. So we get 1 electron group. Okay.
That's considered not around your carbon.
Sorry, what?
The pi bond isn't considered around your carbon.
Interesting question.
We're just around both of them at the same time.
But by that same token, a sigma bond is going to be around both as well. So it's what electron groups, the around would be more in this case on the periphery, not necessarily surrounding the carbon. Okay. What's the bond angle? So our bond angle here. Okay. We've got 3 electron groups, which means what hybridization? We've got sp2. What does that mean about the bond angle? Looking at 120 degrees. Okay? Close enough, right? Okay, any questions about that? Okay, so, So let's take a look. Wait, what? Oh, I skipped ahead. So, next thing that we could go through and do is take a look at the orbital diagram of it. So we look at our pi system for our double bond. You'll notice we use solid lines for the backbone of drawing out our structure. Why do we pick the solid lines? Because those bonds are all in the exact same plane. Okay? So it doesn't make sense to use wedges and dashes, though we could. Okay? We're saying that all of those bonds are in the exact same plane, so we can go ahead and use the solid line. If it's sp2 hybridized, we have p orbitals on those carbons. Those p orbitals are not the easiest to see. Okay? So we could go through and try and draw them on. Okay? We could shade the one in back. And they would be perpendicular to the plane of the atom. Why would they be perpendicular to it? Trying to maximize space. We're trying to give those orbitals as much space as possible, get them away from other electron groups. Okay? So we could draw it on like I did there in red, and it looks pretty awful. Okay? So we could go through and try and do it digitally. That looks a little bit better, but not a whole lot better. So the next thing that we could do to try and visualize those p orbitals is take our structure and we want to just rotate it. Okay, so it comes out at you a little bit. So if we take a look at these 2 hydrogens, and where my hand's located, as soon as we rotate that structure, where are those hydrogen atoms now? Okay, one's coming towards you and one's going away. that rotation, our p orbital that was now coming in and out of the plane is now in the plane, so we can see it a little bit cleaner. Okay? So if we want to rotate the structure so that we can see the p orbitals cleanly, we will shift to using wedges and dashes with our double bonds. Okay? Because we're trying to visualize the structure so that we can see a different part of the structure. Okay? Because I don't remember if we talk about this. In fact, I do remember we do talk about it later, so we'll come back to that. Okay? Does that make sense? Everybody comfortable with the visualization on that? The overall rules? Like I said, we're trying to ease in slowly right now. Okay? What happens when we move to an alkyne? Okay? So alkenes and alkynes end up being very, very related to each other. Okay? So we're not going to look at a lot of alkyne chemistry, but what I do want you to recognize is that the chemistry that we see from an alkene ends up being very similar to the chemistry of an alkyne. So if we were going to go through and draw out a Lewis structure, what would our Lewis structure end up looking like? Okay, we're going to end up having to use a triple bond in between our carbons with our hydrogen on the outside. Okay? What does that mean for us? Well, we can now go through and again look at some of the other pieces. Switch. How many electron groups do we now get around the carbon? We get 2. What's the bond angle? Now we've got 180 in our hybridization. sp. Okay? So just like we did with the alkenes, we could go through and look at an orbital argument. Okay? The problem with the alkynes, or one of the things that's going to make it a little bit more difficult, is with the alkynes to form each of those new multiple bonds, we have new pi bonds. Okay? So our pi bonds, we've got, it doesn't really matter which ones we pick, but I'm going to pick the top and the bottom here. We've got a pi bond there and a pi bond there, and then we also have the sigma bond running through the middle. Well, how do we make the pi bond? Using p orbitals. Okay? Parallel p orbitals. Well, how do we make the other pi bond? Same thing. Can we use the same p orbitals? No, which is one of the reasons why our hybridization changed too. We went from being sp2 to sp. There's 2 leftover p orbitals. Those p orbitals are going to end up being perpendicular to each other. So we could go through and show the same p orbitals that are coming in and out of the plane at you, like we do with the alkene. But then to show the other pi bond, we have to show another set of p orbitals. Those are now in the plane. Okay, and that's what this structure is trying to show. Okay? When we look at either the alkene or the alkyne, okay, this is going to push a little bit further along, but let's go ahead and just think about it. So if we take a look at the alkene, okay, what's going to be the most reactive thing for each of these compounds? Do we expect a lot of reactivity? Why would we expect minimal reactivity for either of these? Just carbons and hydrogen. And the carbon-hydrogen bond is a covalent bond as far as we're classifying it. So we don't see a difference in electronegativity. We don't see a dipole. We don't see partial charges. Okay? So we lose a lot of that obvious reactivity. So now the question is, well, would we expect these to react at all? Okay, yes. What makes these reactive? It's that pi bond. Why is that pi bond more reactive? Okay, it's a source of electrons, but there's a source of electrons in each of the carbon-hydrogen bonds.
It's not as strong.
Why is it not as strong?
Because
Getting to the right idea.
it's higher energy than
Okay, why is it higher energy than a sigma bond? What's that? So what makes the pi bond is a p orbital. What makes the sigma bonds? Some hybridization of an s orbital. The s orbital is lower in energy. We would predict the sigma bonds to be lower in energy and hence less reactive. The pi bond is made up of p orbitals. Our p orbitals are higher in energy. We would expect them to be much more reactive or more reactive. Okay? So that's an energy argument. What about the availability of those electrons? Okay, a sigma bond is located in between those two atoms, so buried in between it. Where's our pi bond? It's out on the outside of our overall structure. Okay, so those electrons are now further exposed to the elements. The more exposed they are, the more likely they are to react. Okay, so those p orbitals in that pi bond is what's going to make these compounds reactive. Okay, so if we've got p orbitals in the alkene and p orbitals in the alkyne, we would predict their chemistry to be fairly similar. Okay. Okay. The textbook does address this, so I kind of want to address it really quickly. What's the hybridization for each of these? Top three. Our central carbon has 4 electron groups. We're looking at sp3 hybridization. What bond angle do we get if we have an sp3 hybrid? We get 109.5. Okay, and this is pretty much everything I've told you, and it's all I really want you to know. Okay, well, we're going to look at a tweak here in just a second. What about the bottom structures? What's the hybridization there? sp2, which means our bond angle is 120. Where do those bond angles come from? Kind of comes with the geometry. It's the electrons repelling away from each other. So when we look at our classical tetrahedral structure, okay, CH4, it's each of those electron groups in those bonds repelling as far as they can away from each other, generating that space, okay, generating that shape or arrangement of the atoms. When we move to boron, okay, it's also an sp2, or it's now an sp2 hybrid. We look at the 3 bonds that boron has here. They're also going to do the exact same thing that our tetrahedral hydrogen bonds do. Okay? They're going to try and occupy as much space as they can. So they're going to get as far away from each other as possible, which means we end up with our trigonal planar or our 120-degree bond angle. Okay? And when we go through and look at the rest of these, we might say that we would expect the same thing. We only look at the number of electron groups. Okay? But are all electron groups considered the same? Okay? What's the difference between them? So we move from here to here. What changed? Hydrogen versus CH3. We're changing the size and electronegativity. Okay? Electronegativity can have an effect, but size is going to become more important. What's the difference between hydrogen and CH3 as far as size goes? CH3 is bigger, which means it has more electrons. What do those more electrons want? More space. So what happens to that bonding? Do I expect the angle, so let's go ahead and highlight it now, that bond angle to get bigger or smaller? Should get bigger, because that CH3 is occupying more space, pushing the smaller hydrogen further away from it. So that angle is now slightly greater than 109.5. What happens to the one down below? It now has to get a little bit smaller than 109.5. What happens when we move all the way out to this last one? What's our difference?
Does it matter what's attached to the carbon, or is it just the atom attached to the bond that makes a difference? Like there's a carbon and 3 hydrogens. Does the mass of those 3 hydrogens matter, or is it just the carbon?
I'm not sure I understand. Let's identify the difference first. Let's work from there. What's the difference between that last structure and any of the other two? Bromine's bigger. Okay, so what would we expect to happen to this bond angle now? Okay, we would expect it to get bigger, right? Okay, because of that bromine occupying more space. Okay, so let's go back to, this one might be a stretch. I don't know if I expected you guys to know this difference. So let's see. Everybody tell what structure this is? Okay, we just now switch bromine for chlorine. Okay, which bond angle would we expect to be bigger? okay, with the bromine, which means what happens back here? It gets smaller. Which of these two reacts faster in an SN2 reaction? Yeah, I know. SN2 was steric hindrance, backside attack. So we're looking at a nucleophile coming in and attacking from the backside of these. Which one would we expect to react faster? Okay, so we're hearing a couple different answers float out here. What's the reasoning on the bromine? Did I hear him say bromine? So if it moves the hydrogens down, what happens to the backside? So if we take a look at this, this is our atom, our bromine, and these are our hydrogen bonds. And this angle gets bigger. What happens to the backside? Harder to get in. Okay. So yeah, we've got to be careful on where all these geometries are coming in. Okay? So the backside attack becomes more difficult as this group crunches down on it. Come on, people.
I didn't.
Okay. What's the actual answer? Okay. If we said bromine makes that backside attack more difficult, we would expect the chlorine to react faster. What's the answer? Bromine. Why does bromine react faster? Is there another effect going on here? It's bigger, and it does have to do with bigger. What's the issue with bigger? Still has to do with size. It's a tricky one. If we take a look at an individual bond, what determines our bond length? How do we measure bond length? Center of the nucleus to center of the nucleus. If bromine is bigger, where's the center of its nucleus? Farther away. So while bromine may be larger, we're putting the same electron density really far away from the carbon. Okay? So what does that do to our bond? If I now take my bromine and move it further away, what does that open up in here? More space. What do these groups of electrons want to do? Fill that space so they expand outwards. What does that do to the backside? It opens up the backside. Okay? So there's lots of effects going on with our different bond angles. Okay? And it's a tricky subject to get around. Okay? When we first move from our hydrogen to our carbon, okay, we don't see that much of a size difference. Our bond length doesn't really change much. When we move up to bromine or chlorine, those atoms end up being so much larger that we end up changing that bond length substantially. So now that we have a lot more electrons there, we're putting them further away. The further away they get, okay, the more that bond angle opens up. Okay? Does that kind of make sense? So when we go through and take a look at our alkenes, what does that mean about the bond angle in our alkenes? Would we expect those to be exactly 120? No. Why not? Are they three of the exact same bonds, or electron groups for that matter? No. They are slightly different, which means they're going to occupy slightly different space. Okay? The book talks about this briefly. I want you to be aware of it. We can see some applications, particularly when we just looked at one, looking at the SN2 reaction. Okay? But I'm not going to directly test you on it. I want to make sure that you're aware of what's happening. So when you read it in the book, if you read it in the book, you know what they're talking about. Okay? Does that make sense? Okay. So what you're responsible for is what I've got highlighted down here. Your SP3s are 109.5, SP2s 120, SP 180. Okay? You should be comfortable with those already. That shouldn't be a big change. I just want to make sure you know what's happening with those when you see them again. Okay. The next part is looking at alkene nomenclature. Okay, so we've got the summary that we've already gone through. I didn't change some of the bolding on it. The bolding is supposed to be functional groups you've already seen. We haven't talked about the alcohols or the amine functional groups yet. We'll see those in a little bit. But our alkenes, our big change for that, we changed the ending to an E. E-N-E. Okay, what was our starting with? We started with alkanes. Our ending was an. Some of the names actually make sense with what our suffix. That suffix is. Okay? So our alkenes, the ending of our name shifts to an "ene," and then we'll go through and name it as we would other things. Okay? So we want to find the longest carbon chain that contains the double bond. Why do we want the longest carbon chain that contains the double bond? What's that? Kind of. What's in red? It says priorities. Okay, so the functional groups you know, we've got alkenes, alkanes, and alkyl halides. Which of those is the most important? Alkenes. So when I go through to find the longest carbon chain, I want to circle the one that has the most important functional group in it. As far as we're concerned, alkenes are the most important at this stage. Which means when you go through and find your longest chain, make sure you find the chain with the alkene in it. Okay? Once you've got that highlighted, you can go through and assign your prefix. What the heck? I think it's prefix, or I'm calling it a suffix. Your meth, eth, prop, bute, pent, hex. You guys remember all those? Okay? And then we'll ignore the halogens and ethers for the moment. Okay? Halogens you should be able to add on as a substituent. We can then number our chain, giving our double bond the lowest number, just like we did with our halides, okay, or our other substituents. We always want to use the lowest numbers possible. This is organic chemistry and we hate math. Okay? So pick smaller numbers. We can then go ahead and add the ending to our overall name. That'll be the "ene" ending. Okay, one thing that I didn't add in here. I didn't add. We need to specify where that alkene was located, because depending on the structure, the alkene could be in the middle of the compound or at the end of the compound. Okay, so how do I assign the number? Okay, well, I want to assign it where it first shows up, lowest number possible. So I want to assign a number to my alkene, okay, on where it shows up. We'll look at, I've got a bunch of examples here, I think. Number to alkene, and we'll put that in front of our name. Okay? What if you have multiple double bonds? We'll assign our priorities. We'll go through and assign numbers to each double bond, and we want to set it up so that we use those smallest numbers possible when we put our name together. Okay? Then we can go through, I did say that. It is Rule 4. I can't read. Then we can go through and name the rest of our substituents. So you can circle each of those, or at least that's how I recommend doing it, circling those substituents as a separate piece. Name that substituent, number where that substituent's located. You've already got your numbering system set up because of the alkene. Okay? So it should be just a real quick toss the number in, and then you can put everything together and you've got your overall name. Okay? There's a couple examples in the lower left-hand corner. Can anybody see those clearly? Okay, and we'll talk about those briefly. You might see some common names, and as I stated here, yes, they are confusing, just like all common names are. If you have just carbon and hydrogen, 2 carbons, and a double bond, you'll sometimes see that referred to as ethylene. That's interesting. Okay, why not ethene? So according to our rules, that is how we would name it. 2 carbons. That gives us the F. Okay, we want to assign our numbers for giving a double bond the lowest number. Well, 1, so that's fairly easy. And we put our suffix at the end. We get ethene. Why do we say ethylene? Okay, break the name apart. Anybody see a clean break in it? Yep, I heard it there. We have an ethyl group with an ene, or a double bond. Okay? So some old chemist went through and said, I'm not changing my rules. It's not ethene, it's ethylene. So you have to know ethylene is referring to this structure. Okay? When you move over and look at the next one, you'll see a similar nomenclature system push through. Okay? We get 3 carbons, so we'd go with prop. Okay, we want to assign numbers to our double bond. We could either assign 1 or 2, depending on which way we decided to count, which numbering system works better. 1, so we could go with 1 propene. Instead, we call it 1 propylene. Why? Because I just came up with this, but very likely when this first started, or when the field was first being created, we could only deal with very small structures. Okay, we couldn't deal with larger things. So when we look at this, we see 3 carbons. Well, 3 carbons are propyl. Okay? And we've got an ene as a functional group. That's my old chemist voice. Okay? Does it sound much different? Okay, at least it sounded a little bit different. Okay? I'm not that old yet. So the propylene is how we end up with that name. We move to the next one. What's happening here? We get 4 carbons. What shape does that look like? I'm trying to make that enlightenment. It's an isobutyl. We've got the iso group, okay, which is that kind of fishtail shape at the end, and a 4th carbon. So we've got isobutyl. Okay, oh, but there's a double bond in there. We'll call it isobutyl ene to make sure we've covered the double bond. Okay.
Is there also a way to change 3 carbons? Oh no, it's isobutyl.
Yeah. So it's a common name versus IUPAC. So if we went based off of our rules, what would we say the name was for this? Okay, so let's start with the very first rule. The first rule was longest carbon chain that contains the double bond. How many carbons is that? 3. So we've got prop. We could go through and number this. So we get 1, 2, 3. We could attach our suffix. We get our propene. At position 1, we have that ene. Do we have any substituents?
2 methyl.
How many methyl groups?
Methyl on number 2.
Oh,
2
yeah.
methyl.
We get 2 methyl, 1 propene. Okay. Kind of makes sense?
So if we were to name them, how does that?
No, both those names are perfectly valid. Okay, in fact, I would expect you to do 2-methyl-1-propene, not isobutyl. Okay, if you're one of those people with fancy memories, you can remember isobutyl. Okay, and I'll still give you points. I just won't be happy about it because I wouldn't remember it. Okay, does that make sense? And we will look at some more complex structures in just a little bit. Okay, lucky you, right? Okay, so next one. Oh wait, that looks the same. That's because it is pretty much the same. Okay, except now we're looking at alkynes. Okay, so if we've got an alkyne, now highlighted in red, our ending switches to a YNE. We follow the same rules. I've checked this a couple times. Still can't quite guarantee it, but it seems that alkenes take priority over alkynes. I don't know why that is. Okay? Just be kind of aware of that. We'll want to circle our, if we had both in there, we'd want to include the alkene in our main chain. Okay? If we only have the alkyne, we'll want to go through and identify the longest carbon chain that contains just that alkyne and go through and assign all the rules the same as before. Okay, giving the, yeah, that's what I'm about to fix. I just saw it. Giving the triple bond, copy and paste. One of the nicest things and worst things. Okay, giving our triple bond the lowest priority possible. Okay, and that assumes that the only other functional groups in our structure would be what? Alkanes, ethers, or halides. Otherwise, we would assign numbers based on the higher priority elements. Okay? Kind of makes sense? Piecing it together? Okay, so. Oh, apparently there's some common names with these. Okay, so we do get some common name kind of overlap here. Okay, what did we call this one? The one that we should have said was ethene. Called it ethylene. Why could that be confusing? What's the ending for the alkyne name? Ine, or Y-N-E, right? What does ethylene look very suspiciously like it's including? It almost looks like a Y-N-E. Okay? So the names may sound familiar. Watch out for that. They aren't the same. You may hear them. You may see that Y there and think alkyne. Make sure you apply where that Y is coming from. The Y from an alkyne, that's going to be for solely the alkyne functional group. Where's the Y coming from in ethylene? From the ethyl. It's a substituent on the double bond. There's a different reason for the Y. Okay? Kind of makes sense? Was that a no?
I was thinking you were having alkene companies, so it's like
Yeah.
off when you said alkene,
Threw me off too.
which is one of
Yeah. I just wanted to make sure that you're aware that some of those alkene common names can appear to look like alkynes. Okay? That's where I see the confusion popping up. Okay? So we can go through and attempt to do some nomenclature here. Okay? Let's go ahead and let you work on a few of these on your own first. If you've got questions, raise your hand. Did I pause? No, I didn't. So what I've gone through and done is highlighted the main chains. Everybody get the main chains? Okay. So for that first one, how many carbons do we have? So we've got what name? We can call this pentene. And I heard someone adding the 2 in front. So we could call that 2-pentene. Do we have any substituents? Sorry. Maybe that 1 or the 2 was me hallucinating. Let's say it was that. Okay, we've got the 1-pentene because the ene showed up at the very end. Okay, so we want a number giving it the lowest possible numbers. Okay, where did I get 2? That was kind of bad. We can now go through and look at our substituents. We've got a methyl, kind of a sloppy looking methyl, and an ethyl. What would we number those? 2 and 3. We could put our name together, which I'm not going to put all together. Would we put our 2-ethyl first or the methyl first? Why the ethyl? Why the ethyl first? Alphabetical order. Oh, it burns. I've been trying to sneeze all day. So we'd get 2-ethyl, 3-methyl, 1-pentene. That 1 can be implied, but it's a bit dangerous to get in the habit of implying where the double bond is, because in all of the other cases, it's not 1, and you have to specify that number. Okay? So it's not going to be a bad habit to always specify exactly where the double bond is, even if it is at position 1. Okay? One other thing that I want to address here, because it kind of came up, is where do we put the number? Okay, we can put 1 right in front of our pentene, implying that. The other option, and this usually happens if we have more complex structure with a lot of different functional groups. What we might want to do is specify more specifically what that 1 refers to. Okay, what does that 1 directly refer to? Refers to the ene, not to the fact that we have a pentene, but that it refers to the ene. So what I can do is say, at position 1, I have an ene. There happens to be 5 carbons.
That's the new way of naming it,
So, yeah, new. You haven't seen that yet.
right? My chemistry teacher last semester hated that. He kept saying that that's how we're supposed to do it now.
It depends on the structure. Most people would stick with the one that we just talked about, our 1-pentene. The only time that the pent-1-ene really becomes necessary is when you have a lot of extra functional groups. If you add an alcohol or acids or anything like that. I think more and more people are starting to shift towards it because a lot of our structures are more complicated. They have a lot more functional groups. Okay. That said, our structures are getting so complicated that nomenclature is kind of falling out of importance because we just call our compound whatever we want to call it anyway. Okay. So, I digress. Our next one. How many carbons do we have in that one? That has 5 too, doesn't it? 1, 2, 3, 4, 5. But what would we name this one? Now we'd go with 2-pentene. We've got the methyls. So we could go through and number those individual positions. We've got our 2-methyl and, what was that, 4? 4-methyl. We could go through and call this 2-methyl, 4-methyl, 2-pentene. Bit excessive, so what do we switch to? 2,4-dimethyl 2-pentene. Okay. Next one, what do we have? We got 6 carbons, so we're looking at. I forgot. This is actually what I wanted to address here. How many people are okay with calling it 6 carbons? Saw that immediately and said, "Yep, 6 carbons." How many carbons did you see? Not quite see where you're getting 5. Okay. One thing that we can do, or that makes triple bonds a bit tricky, is what's our bond angle here? It's 180 degrees. And because we tend to imply carbons as just a single point, when we look at triple bonds, those carbons often really disappear. Okay? So what you can go through and do is label each of those carbons first. There's carbon 1, not technically carbon 1, but a carbon, second carbon. There's a carbon right there where our triple bonds, our pi bonds, stopped. That's a carbon. When we shift to the other side, again, our pi bond stops. That must be a carbon. Carbon, carbon. So we get 1, 2, 3, 4, 5, 6 carbon. Okay. The triple bonds are extremely tricky for that. So watch out for it. Be aware that you may lose carbons, particularly when trying to build larger structures. Okay. So make sure you count your carbons when you evaluate. Okay, so we could go through and number this. We would get 1, 2, 3, 4, 5, 6 carbons. We said that already. I just like repeating. We could go with, yep, you thought that was a sneeze. Hexine. Where do we number it? Either way, we could get still 3 hexine. Now the trick, though, which way did we number it? When it comes to our methyl groups, we need to make sure that we number correctly, and only one numbering actually works. Those are all 3 methyls, and if I number from right to left, I would get 2, 2 for each of those methyls, and then 2, 2. I'm going to trust you guys. I heard 5. 5 methyl. If I numbered the other direction, what would I get? 2 methyl and 5, 5 methyl. Which numbering is correct, blue or green? Blue. Why? Lower numbers. Okay? So the triple bond did not determine where our numbering system came from. In this case, came back to the substituents. Why? Because the triple bond was symmetrically located in the very center of the molecule. Didn't matter which way we numbered it as far as the triple bond went. It matters the way we number it when we look at our substituents. So because this name is a little bit more complex, how would we put this one together? 2, 2, I should have done that in blue. 5, trimethyl, 3 hexine. 3 hexine. Okay, make sense? Okay, for these last 2, go ahead and name them for me. Someone was jumping ahead there. What do we get? 2-pentene, and for the next one? 2-pentene. Are these structures the same? How do you know they're not identical? No. How do you know they're not identical? How do you figure out if two structures are identical? Are they superimposable? No. Okay. There is no way that I can rotate these structures to get them to directly overlap. Okay. With sigma bonds, we could freely rotate, but what happens with the pi bond? That pi bond does not freely rotate. So I can't do that rotation to get them to match up, which means these two structures are stereoisomers. So then the question becomes, well, if they have different physical properties and we can classify them differently, and technically they go all the way down to diastereomers, okay, I have to have a name difference. What's the name difference? We're looking at trans, whoops, actually I think it's that, and cis. How did we figure that out? We go back to our double bond and we look at the groups that are added to it and decide where are they. Are they on opposite sides of the double bond, or are they on the same side of our double bond? Okay? So it's the same trans and cis that you may be used to or may remember from your cyclohexanes. It's now just being applied to double bonds. Okay? And for the exact same reason. With the cyclohexane, we could not physically rotate the structure to get those groups to be switched between being trans and cis. Okay? Same thing's happening here. We can't physically rotate the structure because the pi bond prevents it. Okay? So, with our nomenclature on these, trans, like we already talked about, opposite side of the double bond, cis is on the same side. Ideally, what we're doing is trying to find the relationship between those two. We're not going to have to go through and apply this when it comes to our nomenclature. Okay? So our trans-cis rules are going to apply to non-hydrogen groups, and we're always looking for our highest priority. Okay, so what do I mean by that? Well, if we look at our trans one, what we're going to do is take a look at each side of our double bond. Okay, and we're going to assign priority to the atoms attached. Carbon versus hydrogen. Which one's higher priority? Carbon. Why? Right idea. Atomic number. The exact same rules that R and S had. We assign based on atomic number. Carbon has a higher priority than hydrogen. So hey, we'll go through and say that there's a priority difference. We can go through, there's something wrong in the back there? No? Okay, just checking. We'll go through and do the same thing on the other side. That carbon is a higher priority. We can now look across our double bond. Where are our stars? Opposite sides of that last line are on the same side. Let's make it a red line. Stars are on the opposite sides. We're looking at a trans structure. Okay, makes sense? Okay, so this next slide breaks these all down into individual steps. What I just walked through and did. So let's go through and look at a couple of these. And by a couple, I think I'm going to do 2. So we'll cut it in half first. So we'll look at step number 1 as the green. We're going to go perpendicular to the double bond. Our double bond is running kind of horizontal, so perpendicular. We're going to cut this direction. We're now going to go to each half and assign priorities. Okay, or star our highest priority. We don't have to get any higher than just identifying the highest priority. So we're looking at hydrogen versus carbon. Which one's higher priority? Carbon, which means carbon gets starred. Okay, what? I don't know, we're coming back to that in a second. We're deriving it. Let's move to the right-hand side. Which has a higher atomic number, hydrogen or hydrogen? Okay. There is no difference. We can't tell it. So what does that mean? We can't assign a second star. If we don't have the second star, then when we try and go through and cut the double bond parallel, there aren't two stars to evaluate where they're located, which means what? Cis and trans is irrelevant. We do not evaluate that double bond or name that double bond according to the cis-trans rules. Yes?
Does it matter what the rest of the chain is, or just the atom it's attached?
Let's move to... if you don't see a difference, you move to the next atom to look for the next, see if there's a difference in atomic number there, just like RNS.
Okay.
So you only go atom by atom,
Okay.
one at a time outwards until you find the difference. So you're not looking at the size of that overall chain that's attached, you're looking at the atom immediately attached, right? Just like we did with RNS. Let's take a look at, well, that one's kind of boring. Let's do middle right. We cut our double bond in half, parallel, sorry, that's perpendicular to the double bond, and we want to go through and evaluate what things are attached. Let's take a look at the left-hand side. What do we have attached to it? See a carbon.
Oh, we're doing perpendicular.
Do I have anything else attached to that carbon? Hydrogen. So I compare hydrogen to carbon. Which one has a higher atomic number? Carbon, so I can star that. We can move to the other half. What's the atom? What are the atoms attached? Carbon versus carbon. Can we tell a difference? No, so what do? We move out to the next atom and we see hydrogen versus hydrogen. Any difference? No, so we move out to the next atom. We get hydrogen versus hydrogen. Do we see a difference? No. We move out to the next atom. Do we see a difference? No. Can we move out any further? No. Is there a difference? No. How many stars do I have? One. Do I apply cis and trans to this? No. Okay? Does that kind of make sense? So what we're trying to do is evaluate where our double bond is located, and if it has cis-trans or a requirement to name it according to cis-trans. Okay? The other way you might see it referred to is cis-trans isomerism. Okay? That's what the textbook will actually ask. So you'll be given a series of structures, and you have to identify which of them exhibits cis-trans isomerism. So ultimately what it's asking is, can you name it cis or trans? If you can, yes, it exhibits cis-trans isomerism. Okay?
Do you have to do both? Cut it perpendicular and then parallel?
These rules are established to try and help you get through it easier. These are not like our RS where we have to be looking at it from a different position or a particular orientation. Okay? I've only written these rules so that you can have a stepwise process to solving the problem. Okay? If you want to break it up in a different fashion, that's up to you. Does that kind of answer your question?
We'll see. I'm just not sure which types of problems you're going to ask. I'll see if on another one.
Okay. Let's take a look at this structure. Okay. So we'll go through and evaluate again. We'll cut our double bond perpendicular and evaluate the pieces on either side. As can be helpful, let's go ahead and add our hydrogens. So let's take a look at the top side. Carbon versus hydrogen, which is higher atomic number? Carbon, so we can star that. Look at the bottom part, which is higher atomic number. Now cut parallel to our double bond. Are the stars on the same side or opposite sides? Same side, so we might say cis. Can this structure possibly be trans? Okay. This one gets a bit tricky and it might require pulling out a model kit. There is no way that you can get one of those carbons on the other side of that double bond and maintain a cyclic structure. Okay? So while this may be in the cis conformation, does this molecule exhibit cis-trans isomerism? No, because the trans is physically impossible. It cannot form. Okay? So our rings are a little bit trickier as far as assigning our cis and trans go because of that extra rule. Okay? Let's do one that actually works. So this one we would say no to a cis trans. Let's just call it no to cis trans. Move to that last one. Which double bond do we have to evaluate? Kind of a trick question. Both. If you have multiple double bonds, you must specify cis and trans on both. Okay? Which is going to bring up an issue. If we're going to do cis and trans as far as our name goes, and one's cis and one's trans, how do we name it? Cis, trans, and the rest of our name, what did the cis apply to? Okay, but if it's cis, trans, and we put it at the very beginning of our name, it doesn't match out quite right. And the enes are two double bonds, so we'd name it as a diene. So the cis would be in front, cis and trans would still be in front of a diene. We still don't know which one matches to which. Okay? So we need to come up with yet another nomenclature system as far as figuring this out. And that's where we get the next system, R, E, and Z, ultimately mean the same thing, but they are required to be used in a particular situation. Number one, when you have multiple double bonds, okay, that have cis-trans isomerism, you'll need to use E and Z. Okay? The number two case where it's really important is that you have more than two non-hydrogen groups. So our cis-trans really only applies to comparing two groups around a double bond. So when we looked at our ring, we were comparing these two groups to the double bond, or these two groups to the double bond. That's how we could decide on our cis-trans isomerism. Okay? As soon as we move to a situation like this last double bond here, I don't have two groups anymore. Okay? I have a carbon and a carbon and a carbon and a bromine. I've got all sorts of different groups in there. I have to switch to a new nomenclature system that's looking at our E and Z. Okay? We'll pick up there on Wednesday doing that exact problem. Okay? We'll name that last structure in its entirety.